Similar to the multiple angle, we have a half angle now, and so we want to find our general solution first, and then on the interval. It's easier to find the general solutions because then we can plug in n equals 0, 1, and 2 to find it on the interval. So notice that questions 2 and 3, we found the general solution first and then on the interval, whereas question 1, we found the interval first and then the general solution. And that has to do with, are you solving just for cosine of x, or are you doing cosine of x over 2 or 3x or something like that? So let's first isolate the cosine x over 2. We have 1 plus 2 cosine x over 2 equals 0. Subtract 1 from both sides. We have 2 cosine x over 2 equals negative 1. Divide by 2. I have cosine x over 2 equals negative 1/2. So I have to figure out when is the cosine equal to negative 1/2. Looking at the unit circle, when does the x value equal negative 1/2? That happens at 2 pi over 3 and at 4 pi over 3. We then have two values that cosine gives negative 1/2. So to find the general solution, we need to find the general solution for both of these. So x over 2 is going to be equal to 2 pi over 3 and 4 pi over 3, but also consider their periods. So we have x over 2 equals the first solution, 2 pi over 3, plus the period 2n pi. And then we have x over 2 equals 4 pi over 3 plus 2n pi. And we want to solve for x. This means that we need to multiply through by 2 on both of these equations. The general solution then is going to be x such that x equals 4 pi over 3 plus 4n pi. That 2 is getting multiplied to each piece of this equation. The 2's cancel on the left-hand side. 2 times 2 pi gives you 4 pi over 3, and 2 times 2n pi gives you 4n pi. The second equation, same thing happens. 2 times each piece of this equation. On the left-hand side, the 2's cancel. We have x equals 2 times 4 pi is 8 pi over 3, plus 2 times 2n pi is 4n pi. That's our general solution. So now we want to know, what about on the interval from 0 to 2 pi? So let's start out with n equals 0. In the first equation, that means we have x equals 4 pi over 3 plus 0, and x equals 8 pi over 3 plus 0. 8 pi over 3 is greater than 2 pi. That is not a solution. We have 4 pi over 3. You could try n equals 1. If you get n equals 1, you then have x equals 4 pi over 3 plus 4 pi. That's going to be 16 pi over 3. Same thing for the 8 pi over 3. You're going to get way larger. So that's not a solution. So the only solution that we have on the interval from 0 to 2 pi is just 4 pi over 3. We're solving cotangent of x minus pi over 4 equals negative 1. We have cotangent, which is cosine over sine. We have inside the function is not just x, it's x minus pi over 4. And we're solving for the general solution first so that we can then use that to guide us into what the answer is on the interval. Let's first look at cosine over sine to figure out when that is negative 1. I don't have anything to isolate. Cotangent is already isolated. This is saying something equals negative 1. Well, when is cotangent equal to negative 1 on the unit circle? That means that the sine and the cosine are the same value but opposite signs. So either negative sine of theta equals cosine of theta, or sine of theta equals negative cosine of theta. And the only time the sine and cosine are the same values is when you're dealing with pi over 4. And so at pi over 4, they're both positive. But at 3 pi over 4, 1 is negative and 1 is positive. At 5 pi over 4, they're both negative. And at 7 pi over 4, 1 is positive and 1 is negative. Because remember, tangent and cotangent are positive in the first and third quadrants and negative in the second and fourth quadrant. This means that x minus pi over 4 is going to be equal to 3 pi over 4 and 7 pi over 4. And we just need to include the periods. However, tangent and cotangent are pi periodic, not 2 pi periodic. This means we have x minus pi over 4 equals 3 pi over 4 plus n pi, and we have x minus pi over 4 equals 7 pi over 4 plus n pi. And we're going to solve for x. So this means we're going to add pi over 4 to both sides on each of these equations. Three pi over 4 plus pi over 4 is 4 pi over 4 or just pi. So we have pi plus n pi. 7 pi over 4 plus pi over 4 is 8 pi over 4 or 2 pi plus n pi. And notice that these equations are really saying the same thing. This first equation is saying pi times n plus 1. The second equation is saying pi times n plus 2, which if you plug in any n, these are actually duplicates. It's on the same interval. And so our solution set for our general solution is just x such that x equals n pi. Not even n pi plus pi, because it can be condensed into the shortened form that this answer is true at every pi. It's true at n pi, it's true at n plus 1 pi, it's true at n plus 2 pi, and so on. So the simplest way to write this form is to say x equals n pi. Now, on the interval from 0 to 2 pi, if n equals 0, then that happens at x equals 0. Because we're saying x equals 0 times pi. At n equals 1, we have x equals 1 pi. And at n equals 2, we have x equals 2 pi. But that is not in our interval because our interval does not contain 2 pi. We have the answers 0 pi. Looking at this trigonometric equation, I see some powers. And if I think about this as just variables, that looks like something that I would factor. If this was, let's say, 2x squared minus x minus 3 equals 0, I would solve that using factoring. So I'm going to do the same thing. I'm going to factor this expression and then solve it using the zero product property. So if I was going to factor 2x squared minus x minus 3, I would multiply the a and the c term, and I would write down the b term using the x method, which I've mentioned this in previous videos, but if you're unsure how to factor like this, I do have a video on it on my channel. You're more than welcome to watch it. If you factor using grouping or something else, guess and check, that's fine. I just prefer this method. What multiplies to negative 6 that adds to 1 negative is negative 3 and positive 2. I would then rewrite this as 2x squared minus 3x plus 2x minus 3 equals 0. That's x times 2x minus 3 plus 1 times 2x minus 3, which factors to x plus 1, 2x minus 3 equals 0. But in this case, I was saying that x was actually cosine of x. This means that we have cosine of x plus 1 and 2 cosine of x minus 3 equals 0. And I solve these separately. I have the cosine of x plus 1 equals 0 and 2 cosine of x minus 3 equals 0. Isolating the cosine of x term, we have cosine x equals negative 1 and cosine x equals 3 over 2. And we refer to our unit circle to figure out when this is true. Well, on the second piece here, cosine is bounded by negative 1 to 1, and 3 over 2 is larger than that. That is not a solution. We are just using the cosine of x equals -1. Cosine of x equals -1 at pi. Our answer is then pi, because the question said on the interval from 0 to 2 pi, cosine is 2 pi periodic, and so the next solution would have been 3 pi, which is greater than the interval, and the second cosine of x equals 3 over 2 was not a solution. So we just have pi as our answer. We are solving the equation on the interval from 0 to 2 pi again. This is a squared, so if I consider the fact, what if I had 4x squared minus 3 equals 0? How would I solve that? I would isolate the squared and then I would square root. I'm going to do the same thing here. So I'm going to add 3 to both sides. And then I'm going to divide by 4. And I get cosine squared x equals 3/4. I'm going to square root both sides, which gives me the cosine of x equals plus or minus square root of 3 over 4. That is the same thing as plus or minus square root of 3 over square root of 4, or plus or minus root 3 over 2, because the square root of 4 is 2, using properties of radicals. When is the cosine of x equal to positive or negative root 3 over 2? Well, this happens in every quadrant. You're looking for x equal to root 3 over 2. That happens at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. We're not doing a general solution here because we are only asking about the interval from 0 to 2 pi. Now we're solving the equation on the interval from 0 to 2 pi of cotangent x cosine of x equals cotangent of x. That's something similar to yx squared equals y. How would I solve this equation? Well, I would want to get all the terms on the left-hand side in order to use a zero product property. So I'm going to subtract cotangent from both sides. This gives me cotangent x cosine squared of x minus cotangent x equals 0. And then I see that I can factor out a cotangent of x. That gives me cotangent x times cosine squared x minus 1 equals 0. Interesting. What do I know cosine squared of x minus 1 is? Well, remember the Pythagorean identity. Sine squared x plus cosine squared x equals 1. That means that sine squared x equals 1 minus cosine squared x. So I can replace the cosine squared x minus 1 with sine squared x. I then have cotangent x sine squared x equals 0. I can now use the zero product property to solve these separately. I'm going to take the cotangent of x and set it equal to 0, and the sine squared of x and set that equal to 0. Cotangent is the cosine of x over the sine of x equal to 0. Sine squared of x I can square root and say sine of x equal to 0. But if sine is equal to 0, cotangent is undefined. So really, we're not even going to figure out any of these because that's going to cause issues for the cotangent function. So the only time that this equation is going to work and not have issues is when cosine is equal to 0. So x is equal to 0 at pi over 2 and 3 pi over 2. And that's our solution. Sine is equal to 0 at 0 and pi, but even if it solves the sine squared x portion, when you plug in 0 or pi, that would cause the cotangent to be undefined, so that doesn't work. So the only solutions, again, for this equation is pi over 2 and 3 pi over 2 on the interval from 0 to 2 pi. All right, let's solve the equation on the interval from 0 to 2 pi involving cosecant squared and cotangent squared. Cosecant squared is 1 over sine. I don't really want to solve 1 over sine, so I want to use a Pythagorean identity to rewrite cosecant squared. And I know that cosecant squared equals 1 plus cotangent squared. So I'm going to replace cosecant squared x with 1 plus cotangent squared x. 1 minus 1 is 0. I then have cotangent squared x equals cotangent x. And if I had x squared equals x as an equation, I would subtract x from both sides to get this equal to 0 so I can use the zero product property. I'm going to do the same thing with cotangent. And then I can factor. Take out a cotangent from each term, and that gives me cotangent x times cotangent x minus 1 equals 0. And then I can use the zero product property to set each of these equal to 0 and solve. I have the cotangent x equals 0, cotangent x minus 1 equals 0, then cotangent x equals 0 and 1. So when is cotangent equal to 0? When is cotangent equal to 1? Cotangent is equal to 0 when the cosine of x over the sine of x equals 0. Cotangent equals 1 when the cosine x over sine x equals 1. Looking at the unit circle, think about this. For the cosine x over sine x equals 0 and cosine x over sine x equals 1, I can't have sine ever be 0. So I need to rule out the times when y is equal to 0, which is at 0 and pi. Therefore, we can't have x equals 0 or pi as a solution. On the unit circle, cosine of x equals 0 at pi over 2 and 3 pi over 2. And cosine over sine have the same values and are positive in the first quadrant and third quadrant at pi over 4. That means we're dealing with pi over 4 and 5 pi over 4. Our solution set is then each of these numbers because none of them are 0 or pi. Pi over 4, pi over 2, 5 pi over 4, 3 pi over 2.